So welcome to my talk. This is going to be a little bit lighter and is a talk with a project with a manifesto. Okay, so these are the collaborators spread across 4 computer science departments: Illinois, Duke, ETH, and LUMS in Pakistan, and also involving a couple of physicists, Anthony and Greg, who also work as consultants to the high frequency trading industry. Don't worry, that's not our target market though. All right. So let's take the long view for communication here. Over the long time scale, communication latency has improved substantially, right? So from a time when you were using messengers on foot across road networks to deliver messages, and this took months at a time, we went down to days using pigeon networks. And it's easy to think that this was some medieval times, but actually this is from the 19th century, right? 120 or 30 years ago, we were still in awe of certain other pigeon networks. So this is a British journal complaining about how their pigeon network is so behind the others, right? So it's not so far back. But now we came through the electric telegraph, where this time came down from days with pigeons to perhaps hours between big cities, and finally to the internet. Okay. So now we have messages or even web pages being delivered at 2-3 seconds granularity. But that's no longer good enough. We want more. And this is exemplified by this toy demo that I'll show that my student Debopam created. So here you'll see 2 web pages, the same web page, loaded in 2 different network settings. One will be with a 10 millisecond RTT to the web server, and the other with 300 milliseconds RTT. Okay. So I'll start the first one now. It's working, don't worry. All right, so that's one, and I'll launch the second one now. It's easy to tell which is which, right? So the one on the right is the one with the 10 millisecond network RTT. So in this example, we've exaggerated the difference between these 2 scenarios to be on the order of seconds. So it's sort of obvious why this matters. But actually, we have numbers from web giants saying that people care subconsciously or consciously about milliseconds now. So this is the world we are in, where a few hundred milliseconds impair the user experience so much that people actually abandon their shopping cart on Amazon. They do fewer searches on Google or on Bing, if anyone uses Bing. So we really do care about milliseconds now. Here's another toy experiment to see how poorly we are doing on this benchmark in terms of latency. So we'll do a wget for this page, right? Simple web page. The fetch size is 60 kilobytes, and it takes 720 milliseconds. And this is from my machine in Zurich. We ping this web server that corresponds to this website, 54 milliseconds ping time. Okay, not bad. And if you look at where this web server is hosted, it's in Moscow. And the Zurich to Moscow round trip distance is 4,400 kilometers. So if you had the internet work at the speed of light in vacuum along this shortest path distance, this would be the latency that you'd see, just 15 milliseconds. So in this example, the inflation over this, what we'll call C latency, that's the speed of light in vacuum travel time along the geodesic between the 2 locations, is about 49 times.
How much of your 720 is local OS stuff writing to this?
Some, but not much. In these cases, it's 2-3 milliseconds is the ballpark, unless you're running something from 1980, probably still small. Okay. So I want to emphasize that this is the benchmark that we are going after. You look at the round trip distance between the 2 points, the geodesic, the shortest path round trip distance along the Earth's surface, and you use the speed of light in vacuum to travel along it. That's the C latency benchmark we are chasing. Unless you suspect that the previous example was an outlier, that's really not the case. So we fetched 1 million popular Alexa websites, just their landing pages. So this is not the entire web page. This is just the tens of kilobytes usually of data that form the landing page HTML, right? So it's one fairly small object. That's what you're fetching. From a variety of locations, Planet Lab is what's being used in this experiment. The paper has experiments from actual end hosts as well. Yeah.
So I'm not sure when you're going after Alexa and you're browsing static content, then
sure.
You're basically testing Akamai. not the website, right?
Sure, sure. So, okay, there's a little bit of subtlety here. As of now, Akamai doesn't do full site delivery for most websites. So there's two different models of using Akamai or CDN if other people are unfamiliar with this. Typically, you go for the landing page to the web server, the origin itself. And then that HTML that comes back to you redirects you saying, okay, the object is actually not cnn.com/abc, but cnn.akamai.com/this object.
Ankit, I'm not sure that's true anymore.
No, this is true.
Yes, right. So if you switch to HTTPS, you really don't want to do the
cross-origin thing. Yeah. This is still changing, but as of even a few months ago, I've talked to Bruce Maggs about this. Very small percentage of sites is actually using full site delivery over Akamai. And how this works often is that they're sharing keys with Akamai. So there's a surprisingly bad key ecosystem going on there. So that's how that problem is sidestepped.
But the media you're using is not supporting the speed of light, so you should divide by 5 your.
Sure. We'll come to that. So this is not. So we are not using vacuum to communicate, but fiber, and we'll come to that as one of the factors involved.
Could you just clarify what is the goal here? What is the what are you trying to achieve?
We'll get to that shortly. So far we have just looked at toy experiments, and I'm getting to the point here slowly. Admittedly, too slowly perhaps. So in the median, it's 37 times slower than where we should be. So this is the gap we want to eliminate. We clearly have a long way to go. As the question was pitched already, what will it get us? Why do we want to do this? So we are trying to reduce this 37x gap, but what will eliminating it get us? For one, applications that are already interesting but sort of limited to niche settings today will become a lot more practical and fun. So everyone won't have to sit in a giant room to play a massive multiplayer online game. You need 20, 30, 40 milliseconds of latency for this to be fun, for this to not have significant differences between performance for players. You can extend this over wider areas if you have lower latency. People have been talking about virtual reality, and today you're talking about the scenario where the server that's producing this virtual world is sitting next to you. What if you want remote immersion? You want to be in a different location and get that data and be immersed in that world in real time, perhaps.
But I think a valid question that was already asked is,
Sure.
What are the proportion of network delay and latency
Sure.
in the overall end-to-end?
Absolutely. So for example, this is a particularly good slide to bring up that question on, right? So even the screen refresh time might be 10 milliseconds or so, right? So the standard monitor gives you 16 milliseconds. With the faster displays, you can get 8, maybe some high-end ones 5 or so, I don't really know. But there's an envelope that's from the network and some envelope that's coming from some damage to the latency envelope that's coming from end system overheads. Yes, that's true, but those overheads are either not in our hands as network engineers or improving on their own, right? So display latency, as I mentioned, is improving over time. What we can do is enhance the rest of, so if you have a 50 millisecond budget to do something, we can decrease the network's contribution taking that budget away. So if today you draw a circle around Jerusalem to encapsulate all the people you could reach with your multiplayer game, if you reduce this network latency, then you can expand that farther. That's it, right? So regardless of how the other overheads change, you can expand this budget. So you might not, in the end, achieve just speed of light performance from the application perspective end to end. The network is what's operating at speed of light. That's the only thing we are targeting in the project. Okay. Another example application is online collaboration in music. So again, for this application, 20 to 30 milliseconds, and even experienced musicians can't keep time, right? So this is the kind of application that will really benefit from this. So in summary, a speed of light internet would enable tele-interaction. So this long-standing dream of computer science, computer networks in particular, to bridge distance between locations seamlessly. Apart from that, of course, apart from these applications which I described and others along these lines, you can also expect the unexpected. The internet was not supposed to be what it is. This was not its intended goal, but look at where we are. So hopefully people will build new fun stuff if this happens. There's also a couple of exciting paradigms this exposes, one of which I'll talk about in a bit more detail. This is the illusion of instant response. here's what I mean by this. If this is dependent on the limits of human visual perception. So if you see your screen change within 30 milliseconds or less, then you see no wait time. So if you clicked a link on your web browser and the result was there within 30 milliseconds or so, then you'd feel like magic. It's just there. It's as if the thing just appeared on your screen from nowhere, right? So this would be a significant threshold in user experience. So this is the kind of possibility that is out of the reach without doing something like this. And 30 milliseconds is actually quite a large distance. Speed of light is fast. Okay, speed of light in vacuum. Centered at Zurich, you can reach not only Israel, but places much farther away, round trip. So all of this blue region is round trip reachable from Zurich within that envelope. So this is why, for all of these reasons, I think a speed of light internet should be something that networking people should think of as a grand challenge. So this is something that we should set our sights on. If all of this is so exciting, the immediate question is, why are we so far from the speed of light? This is the big question before us. So the summary short answer is because all of these applications, the way they're architected, they require many long RTTs if you're talking about web page delivery, for example, between a client and a server. And yes, CDNs help remove some of that, and we'll come to that later. So we've broken this down a little more in detail. Here you're looking at that same 37x aggregate number I showed earlier, and it's broken down into its various networking stack components. So you're doing a DNS lookup that costs a certain amount. You're doing a TCP handshake, sending a SYN and getting an ACK back. You're sending your request to the server. It's taking some end host overhead time to compute the result and send it back to you. And then it's transferring that data to you over multiple round trips with the TCP protocol, right? So the data set for this is available publicly, by the way. You can check it out. And we also have in the paper measurements from actual end hosts. Yes, these measurements were collected from Plant Lab. Plant Lab is not representative of actual end host systems. It's university-based infrastructure and all of that. But we have data based on measurements to Akamai servers as well from actual end clients across the world. And it's pretty similar on the broad horizon, except these numbers are even worse because of additional last mile latency. So in summary, we are this far not only because of all these protocols, but actually if you look at just the base infrastructure. So think of this as just the RTT, right? So a TCP handshake, two-way, you send the SYN and get the SYN-ACK back. That's 3x, 3 to 4x, depending on geography, worse than what you would get with this baseline. So just the infrastructural latency, just the RTT itself, is 3 to 4 times worse. And underlying all of these protocols is the same thing. So every time TCP makes 3 RTTs, you're paying this cost also. Apart from that, it's making 3 RTTs, 3 of those. Okay, so this picture often hides this aspect when people think about how the network stack affects latency. What's hidden is the infrastructural latency is also important. So what you really want is a single RTT at C latency. So both of these are the components. So again, I remind you that the C latency here is the lower bound implied by speed of light in vacuum along the geodesic. And coming back to that point about CDNs, why is this a meaningful goal? Don't CDNs already solve this problem? Well, CDNs do help. The traditional model is that the client gets the HTML from the web server redirects it to the CDN node, and subsequent interaction takes place over there. This does solve the problem in some cases to a limited degree. However, if you look at CDN traffic today, even for the typical web request, you will often have the CDN server contact the origin for additional information based on personalization of web pages, dynamic content, all of that. Second, for applications where two parties are interacting with each other instead of a client-server model, things like gaming, the CDN really doesn't give you much apart from the transport or other optimizations that they might be able to do. So this is why the single RTT at C latency goal continues to be important and interesting. Breaks down neatly into these two components, single RTT and C latency, as I mentioned. And I'll describe projects we are working on in both directions. So I'll start with the infrastructure piece of this, which is the C latency bit here, designing a speed of light internet infrastructure. So first, we've looked at this claim that I made about infrastructure itself being slow. The RTT itself is 3 to 4 times longer than it needs to be. Why does that happen? There are several reasons for that. One is the internet's routing. In this example, I was moving data between 2 locations in Poland, and this is what I saw in my trace routes. It first goes to Frankfurt, goes back to an ISP in Poland, goes back to Frankfurt and back again, and then it's delivered. Right, so internet routing does suffer from such anomalies every now and then. It's not geared towards providing you shortest paths. Second, even if you do have the shortest internet path, and this is the abstract view of the path you have, the realities of fiber layout are quite different. So between any 2 successive routers, the fiber is not laid along the geodesic in general, right? Lastly, you have the fact that, as was brought up, we are not using vacuum as the primary medium of communication. We are using fiber, and the speed of light in fiber is roughly 2/3, depends a little bit on the fiber itself, roughly 2/3 the speed of light in vacuum. So some of these factors seem quite fundamental. The question arises, could we actually build a speed of light internet? Well, in some niche settings, this is already being done, and this is where the HFT folks come in. We can steal their technology, right? So in the Chicago, New York market, for example, there's a stock exchange here and a commodities market here, and the traders have an interest in getting messages as fast as possible to the other end. This started out with building fiber routes, optimizing those fiber routes to get as close as possible to the geodesic, and finally to the point where they have deployed microwave towers, a series of about 20 towers for this distance of about 1,200 kilometers, so that the medium of communication is actually vacuum. Or it's not vacuum, but the speed of light is the same as speed of light in vacuum.
And they rent it for $100 million a year.
They rent it for a lot of money. We'll get to the economics. Yes, economics is important. We'll get to that point quickly. So the benefit of this is sidesteps all of these difficulties that we saw earlier. So if you could use this technology to build a wide area network, that would be interesting. Why does this not do that already? It's not as simple as just taking this and sort of putting this at various places and you're done. This is not a network that's shared, right? So this is dedicated to a very specialized application. There's no sharing. There's very fine-grained control over who's sending data to whom. It's just one link, one pipe. So how do we do this? Several interesting questions arise. The first of which is, how do you build a wide area topology with this that's cost effective? So here's one plan that we've been working on, and this is one space where this work opens up some possibility, some interesting scope for algorithmic research. How do we design wide area topologies that make use of these fairly expensive links very well? So this is a map showing every black dot here is a microwave tower, something that already exists in the US. We just use tower data from the FCC in the US. Anytime you build a tower above a certain height, you have to register it in a database. We pull that database and use that to do this optimization. And the color coding here is as follows, that the links that are blue have a baseline load. So you just need one series of towers, and you can deal, we'll get to the traffic models and all that. You can deal with a certain baseline load. For some segments like this Chicago area segment to LA metro, there's a large traffic volume. The traffic model here is population product of cities, right? So you need much bigger pipes. So you might need multiple parallel sets of towers. And this analysis accounts for several factors, Earth's curvature, all of these coming from the physicists, down to capacity limits, which barely makes it to the screen, quite fittingly or not. What this gives us in the end is a network that performs at roughly 5% more than the speed of light benchmark we are after. And it does so at fairly reasonable cost. So as you increase on the x-axis the aggregate throughput of this network, gigabits per second, the cost scales down, right? So it becomes more and more cost effective as you add more capacity to the network. This is cost per gigabyte. Of course, the absolute number is increasing, right? And this is across 3 different traffic models. One is user to user, which means population products between big cities in the US. Okay. The other is data center to data center, where you're connecting 6 Google data centers via such a network and just doing traffic between them. And each of them is the same uniform traffic across these 6 sites. Then there's user to data center. You have these 6 facilities, and you map each big city to their nearest one, and then weight it by population. Okay. So these are the various traffic models. For each traffic model, the result is quite similar. The user to user one is more expensive. There's a large number of endpoints to connect. Okay. But in sum, you can provide under a dollar for every gigabyte at pretty low aggregate throughput. And as you increase the network's capacity, this number improves. It's worth noting that this is still a large way off fiber. So this is about 400 times or so more expensive than fiber. So we'll get to that also shortly. And this was brought up earlier as well. You can run this network pretty close to its design capacity as long as you keep the load under, say, 90% or so. The delay doesn't increase much. So you don't get killed by congestion is the essential point here. It's also not, this analysis is not highly sensitive to deviations from these traffic models. So we have tried adjusting the traffic matrices. You design the network with a certain traffic matrix in mind, and then that traffic matrix is off by 20-30%. The general results still hold. The different constraints on tower height and tower distances. So how far apart can you have 2 of these towers? If you are only able to use towers that are 70 kilometers apart instead of 100, does that impair the network entirely? The answer is no. Unless you get to 50 or so kilometers, it doesn't change the analysis. And that's beyond the reach of today's equipment. Minor changes in the cost model, again, maybe we are $100 million off. For a research project, I think that's okay. The goal is to build this, but the implication, the hopeful implication is that $100 million will not be the impediment to this vision. Okay. If you compare that number, the numbers we are looking at here, one single fiber cable is being laid right now between Tokyo and London through the Arctic Circle. That's costing about $1 billion. So in this space, a few $100 million are really not that much investment. So this is the key question we come to now. So I said that this network provides much smaller capacity than fiber, right? And capacity is about 400 times more expensive. So this is the deal. You have to use the limited capacity to benefit key applications that you care about in a targeted way. What helps here is that a bunch of, and this is the best slide to welcome Keith Finstein at, the bunch of traffic on the internet, 70-80% is streaming video, and his talk will be about that later in the day. A very small slice of this is internet interactive traffic, and this is what we care about here. Okay, so you can get meaningful benefits, and even within that traffic, even within the small percentage that is interactive, you can do smart things like you set just the DNS requests over this network, or you just do handshakes over this network, or you send, as a client who's querying Google, you send your query over this network and get the response back over the standard fiber path. So there's a lot of interesting potential here. So we've done some simulations based on these ideas. Here's application layer benefits for fetching small objects as the network is operating at 1/3 of the conventional routes latency. So if you are at X latency today, let's say 100 milliseconds, what if you went down to 33% of that? So just 330 milliseconds. So this is what it looks like. In the median, you have 49% lower fetch times for these small objects. And if you have single packet objects, this is something like 60%. The ideal improvement, just to remind you, would be 67% in this case. And this is where the end host overheads come in. So this is part of that. For web page load times, you can reduce them by 31% lower. And this is again because web pages, so you don't see the entire 67% because web pages are complex objects with many dependencies and such. Okay. And there's some constant times involved there. The web server is going to take some time in issuing responses, etc. So the summary of this is as follows. So you can build a network that gets you pretty close to that goal. It's not exorbitantly expensive. The cost is actually somewhat reasonable. If an end user wanted to have such a system for playing full-time games, it would be something like if you're a really dedicated full-time gamer at home, the cost would come to something like $4 a month or $8 a month, something on that order, depending on the actual cost numbers. So not something that most people will not be able to afford. And the applications we've simulated so far, lower page load times, tens of milliseconds faster gaming. The measurement data that backs up the analysis I presented earlier about the infrastructure and protocols contributing to end-to-end latency is online, and you can check that out. What are we doing now? There's a bunch of questions we are addressing here about whether the initial result does say that weather does not have much of an impact. So one might suspect that these microwave connections, they are susceptible to weather disturbance, right? So if you have very heavy rainfall, the link gets attenuated and you don't see much throughput out of it. But at least so far, we have not seen a significant impact of this by analyzing a year's worth of data from the US geography. We're still working on refining that analysis. There's a variety of cost topology trade-offs here. Again, some interesting scope for algorithmic work here, which we are starting to do now. If you don't try to build this from scratch, the map I showed you, but actually want to do this in a targeted incremental way, what would you get at different levels of investment? Can you get most of the bang for buck by doing, out of those 300 links that were on that map, something like 80? Questions along those lines. How does this work for other geographies? Is the US special in its concentration of big cities across a large landscape? Would this look very different for Europe or for the Middle East or other places in the world? How does this interface with apps? So far, our results are simulation based, but how would this actually work? Does differentiated service allow this to work today, or do we need something extra beyond this, right? How do you do congestion control in this regime? You are separating, you're connecting widely separated cities in the wide area, and the latency you're providing is something like 3-5 milliseconds, and that's the control loop now. But the buffer you're working with is a very small buffer. So does congestion control require really new primitives in this setting? So this is all that. So we're really, I think, at somewhat of a starting phase in this work right now. So now let's switch gears and get to this side of the picture. How do we get to a single RTT? So I want to start by emphasizing that lots of people are working on this already, prominently Google. How much time do I have left? 10, 13 minutes, okay, good. So, so lots of people have invested significant effort into how do we make protocols give us just one RTT between a client and a server. So Quick is the most hot example of this, right? And it's based on a variety of technologies that have been pieced together over the years. This is an interesting model. It will take a while to be deployed. I think Google has already deployed some parts of Quick now and are continually improving their stack. But in the past, their experience has been that web servers other than theirs are very slow to take up all these changes. So their WebP standard, which is royalty-free licensing and everything, speedy, both of these have under a 1% adoption rate by their own numbers, by Google's own assessment. Under a 1% adoption rate, WebP has been available since 2011 or so.
But speed is HTTP2, so HTTP2 is more than 1%.
Is being it's being standardized now.
I think it's done, right?
They're not quite there in terms of deployment, or it's not quite there yet. But sure, so some of these changes will make it, some won't. WebP, for example, has been around for 5-6 years. Still, web servers are not using it extensively.
So I think the biggest single change is TCP fast open.
Sure. So that will be one piece of this picture.
And that's
Yeah.
deployed already.
Yeah.
And
Yeah.
it works with,
In many cases, yes.
I mean, it's deployed because it's in the Linux kernel.
Sure.
So therefore,
Yeah. Some progress is being made, but we'll see a lot more is needed. Okay. So how do we get to a single RTT now is a better phrasing of this question. So here's one possibility, and this is a hypothetical at this point, and we'll see if we can get there by the next 10 or so minutes. So what if every client, when it tried to connect to a web server, what if in every such case, the client could connect to a proxy near the web server and then have the standard today's stack without any changes talk to the web server? So hopefully these RTTs are small, and even if there are 5, 7, 10 of them, they still don't amount to much overall. And then ship the data back over persistent one long RTT. Now this might seem foolish at first glance, right? So how do we ensure that for every such interaction that you want, this works out? What helps out here is the massive consolidation of web servers near a very small number of cloud nodes. So actually, we've measured this, we've quantified this, right? This is what the picture looks like, and we'll get to it shortly. So these are RTTs to web servers in milliseconds along the x-axis, and this is the CDF across 100,000 popular Alexa websites. This is what it looks like from Zurich with just one node. Okay, so some interesting features about this graph. What's this jump here? There's about 15% of the CDF's mass in that one step. So why are 15,000 popular websites at exactly what 19 or 20 milliseconds from Zurich? They're sitting in the same data center, right? So each of these steps, so this step is in particular Frankfurt. So each of these steps actually corresponds to one such data center, and there's several of them. These are the North American ones. This region that's relatively empty is the transatlantic latency, right? And these are other data centers in Europe. So this from Lahore looks much, much worse, about 300 milliseconds in the median, and this is not atypical. So this is actually a well-connected university-based node in Lahore, in Pakistan. In fact, in many cases, the last mile latency in these situations is extremely poor. Something like 100 milliseconds is typical in Pakistan, for example. This is what it looks like from 12 EC2 nodes. So if you just take 12 EC2 nodes, quantify the latency of the closest of them to a web server, and do that CDF, that's about 5 milliseconds. So with just 12 vantage points, you can get to within 5 milliseconds of most popular websites in the median. The tail is somewhat longer, right? 50 milliseconds at 90 percentile or so. So this is what allows us to pursue that model I just described. I'm calling that the content gathering network as opposed to a content distribution network, which is the other way of doing this. So the content distribution network is trying to get close to as many clients as possible, 6-7 billion of them and counting, right? So this is a contrast we'll come down to closer to the end, but this is why it's turning low latency web delivery upside down. So instead of bringing content closer to users, can users go closer to the content? So this is again to reiterate that model. The client makes a persistent connection to this server, a proxy near the web server, does whatever interaction needs to happen here, gets the results, ships it back. Yes?
So, small question here. Basically, this model kind of, in a way, becomes or makes the network more centralized in a way.
That's true.
Right? And in that sense, maybe for now you are enjoying the benefits of like not congested lost hopes.
Yes.
But eventually, when it becomes popular, hopefully it will kind of stop being beneficial.
This is a great point. I should have added the caveat that we are only trying this for things like web page delivery that don't form, again, a large volume of traffic as a percentage of the internet's traffic volume. So this would not make sense perhaps for doing things like Netflix. You're right about that. So
you're saying that it's only about this tiny slot of interactive services, which may become eventually more popular, and then
the trend actually seems to go the other way around, that the extent of video traffic is actually continually increasing. The percentage of video traffic is increasing continually so far.
The number of round trips is an absolute saving, very short, regardless of load.
What was that?
The saving in the long round trips is absolute regardless of load. It's just for the same round trips, they're now shorter.
Yes, that's true. Yes, that's true. So if you wanted to do this at high traffic volume, you'd have to build the network differently, right? So if you wanted to build this for a different application like Netflix, I think it would be prohibitively expensive, perhaps.
The CDNs are doing exactly the opposite. So if
Yes, exactly.
Like this,
Yeah.
it's exactly, they still keep persistent connections and they save the low area.
Yeah. So this is the question we'll come back to in the end. Save that question for the last slide. So how does this work? Very simple proxy architecture. Nothing super interesting here. The client's browser has a local proxy attached to it, sends the request there. That local proxy contacts this remote near the web server thing, which runs a headless browser, forwards the request there. That contacts the web server. You get the result shipped back. Okay. So the reason for the headless browser here is we don't want to do things like wget, etc. These don't have the same semantics as what web browsers do. Based on this, we have collected some measurement results. And this is right now from just very preliminary, just from one location, Lahore, right now. So this is the result with the content gathering network nodes, and this is the default. And for the top 100 Alexa domains, and keep in mind that the default actually does include the CDN. So the default is using the CDNs and whatever default internet ecosystem is to get this result. So with this model, you can get a significant improvement in page load times today, right? So nothing in this requires you to wait for a standardization process or to wait for web servers to catch up and deploy all of this. This is very doable now. You buy 12 Amazon EC2 virtual machines and you get the system up and running. For a random 100 domains out of the same set, you get a 43% improvement. The number is smaller because some of them are farther away.
So how do you know which one to choose?
Yes, good question. So we've done some analysis of the measurements. They are pretty stable. This is what helps, right? So you don't change your web hosting provider every day. So you can create a very easy mapping of 100,000 or a million, if you care, domains to which node you should go to. You can do better than this, of course. So in some cases, you might have scenarios like the client is here, the Amazon node that's closest to the website is somewhere very far away, but actually there's another Amazon node that's, instead of being 5, it's 8 milliseconds, but that's closer to the client. We've not really gone into this yet. Okay. So now the other question is, isn't this very expensive? For every client to maintain this extensive network of proxies on its own would obviously be expensive, but if you multiplex this across users, if you assume that you'll reach a certain scale, you can do this for under $1 per month. And this is based on very, very conservative analysis, like take the most expensive Amazon nodes in the most expensive regions, don't do any parallelization, don't do any optimizations. Just take whatever time it takes for one web page to load 300 milliseconds or something from these locations, and account for that, right? So this number should be substantially smaller.
Did you also account for the traffic cost?
Yes, yes. So this accounts for the most expensive bandwidth as well.
Okay.
So all of the numbers in this are basically like how far could we be?
So are you guys doing a startup? It's like, okay, this is difficult to say academically.
And thinking about it,
Startup is what you need to do with this stuff.
and thinking about it, I'm
in Pakistan in particular.
yeah. So this is on my mind. So I'm seeing. Yeah, we can talk offline about this. So this is the summary of this work. One reason is it's still preliminary, right? So as I said, the results are from one location. This was just at a workshop. We're still building on it. So it would be a little bit premature. So it gives you 43% faster page load time. One thing to note here is that Google's Flywheel actually is doing something philosophically similar. So they are bouncing users. So from the Chrome browser, as they control effectively the client, they can redirect requests to their infrastructure and compress data and push it back. But actually, when we do use Google Flywheel in some experiments, we see a 20 to 30% advantage over Google Flywheel also. And the other thing is our optimizations are actually orthogonal to theirs. So they are focusing on compression, which we are not doing at all. We are not changing web pages. We are not compressing the images down to WebP or anything. It's just as is. So both of these are sort of orthogonal directions to pursue. So we are pushing performance, and this is sort of where we are going, and possibly other ways. So, so the question I want to leave you with is this. These are two sort of very different models of how you could organize web page delivery, or at least for small pieces of content, web content delivery. You can have a CDN that does this with 1,600 plus locations, as Akamai claims, 200,000 plus web servers spread across 1,600 networks in the world. Or you could perhaps do this with just 12 locations in EC2. There's different trade-offs. There's different cost models, right? So this will be, from my perspective, the most interesting takeaway from here. You're still sort of fleshing out what this picture looks like, what the trade-off is there. All right, thanks. I'll take questions. Yes.
In a way, it's sort of a rediscovery of the ancient terminal and computer model.
Yeah.
Sure. Yeah.
Because you're saying let the state and everything be there,
Yeah.
close and
Yeah.
in itself.
Yeah.
We, by the way, use a measure for deciding placement of things of instructions per meter. It's the
Okay.
number of instructions that my laptop can perform while light travels 1 meter in
Ah.
fiber feet. The number
Sure.
is roughly 10.
Okay.
Depending on the computer and fiber or that,
All right.
which helps you understand why certain things you may as well run locally rather than wait for the system
Absolutely.
to go and get it back to the other end.
Absolutely. So in fact, right now we are trying to build a model that has two pieces, right? So one is this CGN node, this latency, and this latency. So you're trying to build a model that captures these three numbers and answers questions in that way. Yeah. Yes.
So we compared in the beginning of the talk the CDF of several protocols to the
Yep.
benchmark.
Yep.
But it seems like in virtual reality applications or game, the designer will want to know how concentrated the arrival rate is, not only
Sure.
the best average time.
Sure, sure. So there's actually two questions buried in here. One is for applications that depend on a persistent connection like gaming or virtual reality, most of the protocol business doesn't matter. In fact, none of it really matters. You just care about the RTD. So the relevance of the project is actually even greater for those applications. And the second question that you're asking is, do we care about the tail or do we care about the average? I think both have their implications, right? So if you're looking at web pages, even the average would be interesting. This is a somewhat different model from within the data center. So within the data center, you're capturing 1,000 different objects to assemble a web page, and the last of them might decide your request, your delivery time. This is not the same constraint model. Here, you're looking at one client you're sending a bunch of data to from the data center. Does performance improve for this client? Yeah, it might not improve for some other clients in the tail. That's okay. Yeah. So the tail effect does exist. It's a different constraint than within data centers, for example.
Let's thank the speaker again.
Thank you.